4.1.5, we have a literal equation. So this is a literal equation because there are all kinds of variables here. So we can still solve for one variable by writing it in terms of everything else that's there, or all the other variables. So remember, our instruction is to solve for x in each of the following. And this, of course, is included in the following. So we need to solve for x in here. So x is it's currently locked up in this whole expression over here, and that is all equal to s. We basically need to just rework this equation so that x is isolated by itself and equal to all the other stuff that is on the other side of the equation. Remember, this is still a linear equation effectively. So we're going to just quickly see what this looks like if we had to try and unlock the x from that square root sign. So the first thing, of course, that you would want to do is to get rid of the square root sign, because we don't like to work with denominators and fractions in the equation. We would like to get rid of that square root sign as well. And the way to do that is to square both sides. So I'll square the left hand side as is squared, and if I square this side, it will look like that. And of course, squaring and square rooting, they are inverse operations, which means they destroy each other basically. So you will just have 2x minus 3t popping out of that operation, and this is still equal to s to the power of 2. Right, so now we can proceed easily to isolate x by getting x by itself, in other words. Now conventionally, we know that we like to work from left to right, so if it helps, I'm just going to swap this whole thing around by writing 2x minus 3t on the left hand side and writing s squared on that side. Just note there's no sign changes happening here because it's a straight swap, so nothing changes in terms of signs. But if you're comfortable continuing working with your unknown on the right hand side, that is perfectly fine. So I'm going to then take my 3t to the right hand side, or add 3t to both sides, and that will then result in s squared plus 3t. And then I simply need to get rid of my 2 coefficient so that x can be isolated. So I'll divide both sides by 2, and that will leave me with x on the left hand side, and I will have s to the power 2 plus 3t all divided by 2, and that is your answer. Remember, your answer is not going to be a number in this case because it is a literal equation. There is more than one unknown. We simply want to write one of the unknowns, in this case x, in terms of all the other unknowns or variables. Some of you would go further by splitting this up and saying x is equal to s to the power 2 over 2 plus 3t over 2, which is not necessary. This point over here is just fine. Right, we are back with 4.2, and this was a simultaneous equation. Solve for x and y in the following simultaneous equations. It's just this one simultaneous equation. So 3x plus 2y equals 4, and 2x minus 3y equals negative 19. We need to solve for x and y simultaneously. I've written it out here and labeled the two equations as A and B. And for the first approach, I'm going to use the method of elimination, which is the simplest method to use, in my opinion, but of course we will need to look at substitution as well. So with elimination, in this case, I have equation A and equation B. I'm looking at my terms in each equation, and I can see that there's no equal coefficient for either the x or the y. In other words, I can't just eliminate the x's as they are because they have different coefficients, and the same goes for the y's. So I'm going to choose, in this case, I'm going to try and get my x's to be the same. In other words, I need to find an LCM for 2 and 3. And that, of course, in this case would be 6. So I'm going to do something to this equation so I can have this as 6x, and I'm going to do something to equation B to get this as 6x as well. And then that will allow me to then subtract the two equations from each other and get rid of those x's. So I'm going to, for equation A, I'm going to multiply equation A with 2. So I'll say A multiplied by 2. So that will give me 2 times 3x gives me 6x, plus 2 times 2y gives me 4y, and 2 times 4 gives me 8. So I'll call this equation C now, because that's a new equation. And I'm going to take equation B. I'm going to multiply it by 3, so I can get 6x there as well. So 3 times 2x gives me 6x. And 3 times negative 3y gives me negative 9y. And 3 times negative 19 gives us negative 57. And we'll call that equation D. So now I have a situation where I've got 6x and 6x, which means if I subtract the two equations from each other, I will have eliminated the x variable, which will allow me to then solve for y. And that's the point of the elimination method. Some textbooks also teach to multiply by the additive inverse of the LCM. Or multiply by numbers such that you get the additive inverse. So if I multiply by 2 in equation A, I would need to multiply by negative 3 in equation B, so I can have a negative 6x, and in that way I can add the two equations to get the x's to be 0. But it's the same as saying subtracting the 2 to get to 0. It's the same thing, so you don't have to do that. So I'm going to go ahead and subtract these two as they are here now. I'll just write on the left hand side here C minus D. I'll put a minus over here. I'll put this in brackets just to note that I'm subtracting this whole equation. So 6x minus 6x gives us 0. And then 4y minus negative y is 4y plus 9y. And that will give me positive 13y is equal to 8 minus 57 is 8 plus 57, and that will give us 65. Then if I simplify, I'm going to divide both sides by 13, and 65 divided by 13 is 5. So y is equal to 5. And now I can take y equals to 5 and I can substitute it into either A or B. I'll choose A, so I'm going to say y equals 5 into equation A. So I'm going to have 3x plus 2y, which is now 2 times 5, is equal to 4. So that is 3x plus 10 equals 4. So 3x equals 4 minus 10, which is negative 6. So 3x is equal to negative 2.